Okay, so today we will start from the result that we discussed in last class. Theorem, you can call as theorem 4 if, or better to use theorem 6. If f is a multiplicative, if f is a multiplicative function, then capital F, which is defined as sum over the divisors of n, fd is also multiplicative. Okay, now move to proof of this result, because we have to show that f is a multiplicative function. So we take two numbers, let m and n be two relatively prime positive integer. That is, the GCD of m and n is equal to 1. Now we have to show that f m times n is equal to fm times fn. Okay. So for this case, we need to find f m times n first. We apply definition here, so which is sum over the divisors of m times n f of d. Okay. So where d is a divisor of m times n. Okay. Now we know that the GCD of m and n is 1. Okay, so they are relatively prime. So if d is dividing the product m and n, it means d completely divides m, okay, as well as n. Okay, so we can partition the numbers which are the factors of m and n. For example, divisors of m are d1 and divisors of d2, divisors of n are d2. So d2 are the divisors of n because m and n are relatively prime. So divisors of m are d1 and divisors of n are d2. Okay, so d1. So due to the relatively primeness of m and n, we say that d1 and d2 are also relatively prime. Okay, so we can write m n equals sum, and we can divide d into the products of d1 and d2 because the divisors of m are different than divisors of n. Okay, So we represent divisors of m by d1 and divisors of n by d2. So this can be written as f of d1 times d2, and this sum runs over the divisors of m and divisors of n. Okay. So we know that this d1 and d2, okay, d1 and d2 are relatively prime, and f is a multiplicative function. So f can be written as, so d1 divisors of m and d2, this must be n. Okay. Divisors of m, f d1 times f d2. Okay. So because d1, this summation runs over the two types of divisors of m and divisors of n, and they are completely different. Okay, because their GCD are not only different, but their GCD is one as well. So they are relatively prime. So we can use double summation here as well, one for divisors of m and the other one for divisors of n. Okay, and there is no rule to which one of them should be used first. You can use any of them first and then second. So d2 runs over the n, and d1 over the m, f of d1, f of d2. Okay, let me separate this one. Okay, so if we use the definition here, okay, so by definition of capital F, this could be written as capital F m. Okay, because sum runs over the divisors of m, f of d1. So this is, so now we can write sum d2 over the n, capital Fm, f d2. Okay, so because there is no d2 here in Fm, so this can be written outside the summation sign, because this summation depends upon d2. So we can write Fm outside the summation. So this will be d2 runs over the n, f d2, and by definition we can use Fm times Fn. So it means capital F is multiplicative. So it means if any function is multiplicative and its sum over the divisors is always multiplicative as well. Okay, so that's the result. And let me define two more functions that we already discussed about Euler phi function, and now we have two more number theoretic functions. One of them is tau. We represent that by tau of n. So what is tau of n? The number of positive divisors of n. The number of positive divisors of n is tau n. Okay. For example, if we consider tau 9. Okay. So number of positive divisors of 9, 1 is a divisor of 9, 3 is also a divisor of 9, and 9 itself. So there are 3 divisors of 9, so tau 9 is 3. Okay. Similarly, tau 12. So 1 is a divisor of 12, 2 is a divisor of 12, 3 is also divisor of 12, 4, then 6, and 12 as well. So 1, 2, 3, 4, 5, 6. So there are 6 number of positive divisors of 12. Okay. Now, the next number theoretic function, sigma. Sigma of n. Sigma of m is the sum of the positive divisors of n. Okay. For example, sigma of 9. So it's the sum of the positive divisors of 9. So positive divisors of 9 are 1, 3, 9. So 1 plus 3 plus 9. So which is 13. Similarly, sum of sigma of 12. So this is 1 plus 3, 1 plus 2 plus 3 plus 4 plus 6 plus 12. So 1 plus 2, 3, 3 plus 3, 6, then 10, 16, 16 plus 12 is 28. So this is 28. Okay. So now these two functions, tau, sigma, and Euler phi function phi. Okay. So we have studied 3 functions. Okay. Or now we are familiar with 3 functions, phi, tau, and sigma. Okay, are multiplicative. So all of them are multiplicative number theoretic functions. Okay, so let's have some results related to tau and sigma. Okay. So this is new theorem, call it theorem 7. Let P be any prime and E any positive integer, then tau on p to the power e is e plus 1, and sigma of p to the power e is p to the power e plus 1 minus 1 over p minus 1. Okay, so it's very important theorem. Okay, by using this result, you are able to find the tau and sigma of any integer. Okay, because any integer can be decomposed by its canonical decomposition or by its prime factors. So because this is power of prime, so if you are able to find the tau and sigma of any power of prime, then you will be able to find the product of powers of prime, because tau and sigma are multiplicative functions. Okay, so before going to that, let's have the proof of theorem 7. Okay, so it's already given here. P is a prime number and E any positive integer. Okay, so the positive divisors of P to the power E are 1, because 1 is a divisor of any number, and then P, because P divides P to the power E, then P square, because P square will also divide P to the power E if E is greater than 2, and till P to the power E. So these are the divisors of P to the power E. Okay, so can you count these numbers? We can easily count them. So this is from P to the power E are E and then 1. Okay, so by counting these divisors, are E plus 1. Thus, tau of P to the power E is E plus 1. Okay. Next thing, sigma of P to the power E. So sigma of P to the power E, so by definition, sigma is the sum of the positive divisors of n. We have positive divisors of P to the power E. So we can find their sum easily. So now sigma of P to the power E is 1 plus P square till P to the power E. Okay. So look at here. So this series is a geometric series with first term equals 1, with common ratio equals P. Okay. And how many terms are here? E plus 1. So this is first, this is second, this is third, and this is E plus 1. So n is E plus 1. We know that the sum of the geometric series is, because P is greater than 1, so ratio is greater than 1. So we know that the sum of geometric series is A times R to the power n minus 1 divided by R minus 1. We can apply formula here. So A, which is 1, times R to the power n. So R is P and n is E plus 1 minus 1 divided by R minus 1, which is P minus 1. Okay. So this is p to the power e plus 1 minus 1 divided by p minus 1. Okay. So by using these results, we can easily find the tau and sigma of any number which is power of prime. For example, tau of 64. So this can be written as tau of 2 to the power 6, and so e is 6 here. So 6 plus 1 means 7. Okay. Similarly, sigma of 64 means sigma of 2 to the power 6, which is 2 to the power 7 minus 1 divided by 2 minus 1. 2 to the power 7 is 128. 128 minus 1 is 127. So sigma 64 is 127. Okay, so without that formula, it's very difficult to compute sigma of 64 by using the other counting techniques. Okay. Okay, now move to the next result. Okay, by using this theorem 8, we can easily find the tau and sigma of any positive integer. Okay, let n be a positive integer with canonical decomposition with canonical decomposition. Canonical decomposition means the prime factorization of any integer. P1 to the power E1, P2 to the power E2 till Pk to the power Ek, where P1 to Pk are distinct prime and E1, E2 and Ek are integers. Okay. Then tau n can be computed by using this formula, product I from 1 to k, Ei plus 1, and sigma of n can be computed by using the product I from 1 to k, Pi to the power Ei plus 1 minus 1, Pi minus 1. Okay, proof of this result is very simple. Okay, very simple and easy. We know that tau and sigma are multiplicative numbers. So if we apply formula over the n, then we can apply tau and sigma over the product. Okay. And in last lecture, we have already discussed that whether we have two or more numbers which are pairwise relatively prime, then the multiplicative function can be distributed among all integers. So look at the proof. So tau n means tau on P1 to the power E1 P2 to the power E2, Pk to the power Ek. Because tau is multiplicative, so it can be, tau is multiplicative, so it can be written like tau on P1 to the power E1, tau on P2 to the power E2 till tau on Pk to the power Ek. Okay. So in our last result, we have derived the formula for tau on P to the power E1, P to the power E. So we have formula here. So this is E plus 1. So E is, because P1 is a prime, so E is E1 here. So we can write E1 plus 1, the result of first tau, the result of second tau is E2 plus 1 till the result of last one is Ek plus 1. And this can, because we have a product here, so we can use the letter capital pi for product, and we can write I from 1 to k and Ei plus 1. Okay. Okay, let's move to the second part of the result. We apply sigma on both sides here. So sigma on P1 to the power E1, P2 to the power E2 till Pk to the power Ek, and this is equal to sigma on P1 E1, sigma on P2 E2, sigma on Pk Pk to the power Ek. We apply sigma individually on each power of prime. Okay, so by definition, by previous theorem, we can apply sigma here. So this is P1 to the power E1 plus 1 minus 1 over P1 minus 1, and P2 to the power E2 plus 1 minus 1 over P2 minus 1 till Pk to the power Ek plus 1 minus 1 over Pk minus 1, and this can also be written in the product form I from 1 to k Pi Ei plus 1 over Pi minus 1. Okay, so that's the proof of the result. Okay, look at the bigger number. For example, 6120. Okay, we need to find the number of positive divisors and sum of the positive divisors of 6120. 6120 is not prime, okay, but it can be decomposed by using the prime decomposition or prime factorization. So 6120 can be written as 2 to the power 3 times 3 to the power 2 times 5 to the power 1 times 17 to the power 1. Okay. So now we apply tau on 6120. It means we are applying tau on 2 to the power 3 times 3 to the power 2 times 5 to the power 1 times 17 to the power 1. So this is E1, E2, E3, E4. Okay. So for tau, there is no need to use the prime number. So E plus 1, E1 plus 1 means 3 plus 1. Okay. If you look at the formula here, so we just need powers only. Okay? We just need powers. So 3 plus 1 times 2 plus 1 times 1 plus 1 times 1 plus 1. So 3 plus 1 is 4, 2 plus 1 is 3, 4 times 3 is 12, 12 times 4 is 48. Okay? And now sigma on 6120, we need some calculation here. Sigma on 2 to the power 3 times 3 to the power 2 times 5 to the power 1 times 17 to the power 1. So this is P1, E1, P2, E2, P3, E3, and P4, E4. So if we apply formulas here, so 2 to the power 3 plus 1 minus 1 divided by 2 minus 1 times 3 to the power 2 plus 1 minus 1 divided by 3 minus 1 times 5 to the power 1 plus 1 minus 1 over 5 minus 1 times 17 to the power 1 plus 1 minus 1 over 17 minus 1. Okay. So 3 plus 1 is 4, 2 to the power 4 is 16, 16 minus 1 is 15. 2 plus 1 is 3, 3 to the power 3 is 27, 27 minus 1 is 26, 26 divided by 2, because 3 minus 1 is 2, so this is 13. And 5 square is 25, 25 minus 1 is 24, 24 divided by 4, so 6. 17 square is 289. 289 minus 1 is 288. 288 divided by 16 is 18. Now you just need to get the product of four numbers, which is 21060. Okay, now move to another multiplicative function. So now we have three number theoretic or multiplicative functions. Okay, Euler phi function, tau, okay, number of which computes number of positive divisors, and sigma, which computes sum of the positive divisors. Okay, the next number theoretic function is called Mobius function. Okay, so how can we define Mobius function? Mobius function is represented by mu. So this is defined on positive integers. Let n be a positive integer, then Mobius function on n can be defined by using a piecewise function. So this gives value 1 if n is 1. Value 0 if square of any prime divides n for some prime p. Minus 1 to the power k. If n can be decomposed by using primes pk, where all pi's are distinct prime. Okay, so it's clear that mu of 1 is 1. Okay, and mu of for example, let me use mu of 12. Okay, so mu of 1 is very simple. Mu of 1 is 1 by definition. Okay, how can we find mu of 12? So this is not 1, so we cannot apply the first definition. Okay, and we cannot apply the third definition as well. But we know that mu of 12 can be written as 2 square times 3. Okay, so because this is n, so this n can be divided by 2 square, and 2 is prime. So this integer n can be divided by the square of a prime. So it means by definition it gives 0. Okay. Similarly, if we have 672, so 672 can be written as 2 to the power 5 times 3 times 7. So 672 can be divided by 2 to the power 2 as well, because this number has a prime factorization or canonical decomposition in which we have 2 to the power 5. So definitely this can be divided by 2 to the power 2. So this can be written as 0. Okay, because 2 square divides this number. For example, we consider, let me consider 26 or 39. So 39 can be written as mu 3 times 13. So we have factorization into primes, distinct primes. Okay, so we have two number of factors here. So here we should apply the third definition. So k is 2 here. So minus 1 to the power k. So this gives you plus minus 1 to the power k. So k is 2 here. So minus 1 to the power 2 is plus 1. So mu 39 is 1. Okay. And look at mu 30. Mu 30 can be written as mu 2 times 3 times 5. So here we have factors of 3 distinct prime. So k is 3 here. So minus 1 to the power 3 is equal to minus 1. So this is the way that we compute Mobius function. So Mobius function has three types of output or three values, 1, 0, and -1. Okay. So any integer, so Mobius function of any integer can give you 2, 5, 1, 0, and -1. So similar to the other multiplicative function that we discussed, means sigma, tau, and phi, mu is also multiplicative. Okay? Theorem, new theorem, the function mu is multiplicative. That is, mu of mn equals mu of m times mu on n. Okay, we are not going into the detail, okay, or into the proof of this result. So, but we have a lemma. Actually, we are targeting Mobius inversion formula. Okay? So, to prove Mobius inversion formula, we need some results prior to that. So, this result, lemma, or you call it lemma 3, is one of them. Let f n is sum that runs over the divisors of n, mu of d, then f on p to the power e is 0, where e is greater than 1. Okay. And we know that mu is multiplicative. So by using the previous, we have already discussed that if this function is multiplicative, then this function is also multiplicative. Okay. So look at the proof of this result. F of PE. Okay. Now we apply the definition which is given here. Sum which runs over the divisors of n, mu d. Okay. And n is p to the power e, so better to use p to the power e. Okay. So which are p divisors of p to the power e? Divisors of p to the power e are 1, p, p square till p to the power e. So if we apply some notation here, so this will be mu1 plus mu p plus mu p square till mu p to the power e. Okay. So now, by definition, we know that mu of 1 is 1, mu of p. So mu of p, so we have to apply the third definition here. So because we have only one prime, so k is 1, so this can be written as minus 1 to the power 1, then mu p square. So p square can be divided by p square. So it means this number or this integer is divisible by p square. So Mobius function on p square is 0. Similarly, Mobius function of p cube is also 0 till, because every number on Mobius, because p to the power e is divisible by p to the power 0. So this is also 0. Okay, now move to next result, which is another result, theorem. We call it theorem. So I think we should write numbers as well. So this is theorem 8, and we should call it theorem 9, and this must be theorem 10. Okay. So statement is, let n be a positive integer, let n be a positive integer, then sum runs over the divisors of n of mu d is either 1 if n equals 1 and 0 otherwise. Okay, so now we can define by we can define the sum of the Mobius inversion function, okay, that runs over the divisors of n. So this could be either 1 or 0. And in previous result, we proved that if we have p to the power e, then this result is 0 here. Okay, okay. Look at the proof. So we have to prove for all positive integers. So if we take n equals 1, so if n equals 1, then sum over the divisors of 1 mu d. So there is only possibility of 1. So mu of 1. So by definition of a Mobius function, it is 1. Okay. So now we have 1 here. So let n is greater than 1. So if n is greater than 1, then it can be decomposed by using canonical decomposition. So if n is greater than 1, then it can be decomposed by using canonical decomposition, which is n equals p1 to the power e1, p2 to the power e2 till pk e to the power ek. Okay? So this is canonical decomposition. And we assume capital F of n is equal to, because we have to compute this one, and we assume that this equal to Fn, so we have to compute capital Fn. Sum that runs over the divisors of n mu d. Okay, so we assume that this is equal to mu d. And we know that mu is multiplicative. So if mu is multiplicative, it means f is also multiplicative. Okay. Then by using the result that we discussed previously, Fn, because mu d is multiplicative, and by the multiplicity of because mu d is multiplicative, so capital F is also multiplicative. So Fn can be written as F on P1 to the power E1, P2 to the power E2 till Pk to the power Ek. Okay. So now this can be written as F P1 to the power E1 times F P2 to the power E2 till F Pk to the power Ek. Okay. So we apply this definition here. So sum which runs over the divisors of P1 to the power E1, okay, or if we apply the this result, Fp to the power E is 0. So we can use this lemma here. Okay, so there is no need to apply this sum again and again. So we have already proved that this result is 0. This is also 0. So 0. So product of all 0 is 0. So it means Fn is 0. Fn is 0 means this function is 0. Okay, for all other values. So 1 when n is equal to 1, we have proved now. And for all other values, when n is greater than 1, so this gives us 0. Okay. Okay, look at the example here. Sum over the divisors of 18 mu d. Okay. So we can verify if we use result. Okay. If we use this result, so by using this result, this must be 0. Okay, by using theorem 10. But we can also verify theorem by the computation. So divisors of 18 are 1, so mu on 1, then 2, then 3, then 6, then 9, then 18 itself. Okay. So mu of 1 is 1 by definition, mu of 2 is minus 1 to the power 1, mu of 3 is minus 1 to the power 1, and mu of 6. So 6 can be written as 2 times 3. So the product of two distinct primes, so this can be written as -1 to the power 2. 9 can be written as 3 square, so this number is divided by divisible by the square of prime, so this is 0. Similarly, 18 is divisible by 3 square, so this is also 0. So 1 minus 1 minus 1 plus 1, so this is again 0. Okay, so uh, that's the verification of the theorem by using an example. Okay, so in next class we will discuss Mobius inversion formula, which is very important, and we will have some examples related to Mobius functions as well. Okay, so inshallah we will meet again in next class. Thank you.